So this is the second time we've given a version of this presentation. We delivered it about 3 weeks ago at Sci5's event in Austin, and we got some very enthusiastic input from the folks at ARM. So this version has a lot more TMs and Rs and modest corrections to it. But the good news is the content is actually that much better for your consumption today. So the reason we're talking about this is when people think of embedded security, they think about TrustZone. But a lot of people don't really understand what TrustZone is and what it composes. And then in the RISC-V space, a lot of customers say, what's your TrustZone solution? Which is hopefully what I'm going to address today. We call it MultiZone, and the good news is it runs on top of all of the RISC-V cores, at least all the ones that I'm aware of today. So let's get into this. So about 3 weeks ago in the security world, the earth absolutely shook. It was actually just the week I was delivering the presentation in Austin. We had a 9.8 on the Richter scale of security vulnerabilities. So this was a Linux vulnerability that checked all the boxes. It was a network attack. It was low complexity. You needed no privileges to do it. You could completely take over a system with it. And this made absolutely no news. I'm guessing none of you heard of this at all. And the reason is because every single day there is another exploitable vulnerability discovered in Linux. So we're up to several hundred a year now. And the challenge with that is there's no ability, even if you're patching in real time, there's no ability to capture and patch these. So if you have a rich operating system like Linux, you should just assume that it actually has already been exploited and it is vulnerable. If you go to something like an RTOS, like FreeRTOS, you're not necessarily better off. FreeRTOS had, I believe, 14 exploitable vulnerabilities discovered in its TCP/IP stack just last fall. So the nature of a rich operating system is it is a vulnerable operating system, which is why we need these security solutions. So the way that we used to make systems, the way that we make rich operating systems today, is we combine a bunch of code blocks together with our compiler and a linker into one gigantic memory image. And that's a super convenient way to write software because it allows everything to talk to everything else. You put something on the stack and you call a shared library, or you have a pointer to the heap and you call a shared library. But the problem is you can't keep secrets in this structure. And an even bigger problem here is the way that code comes together now is a lot different than 30 or 40 years ago. It used to be that most of the code that we wrote came from in-house. But if you look at how code comes together today, most of the code that we write actually comes in the form of libraries. In my last job, I was CTO at an IoT platform company, and as best as I could track it, we had 130 libraries in our FreeRTOS version. I'm not even sure I could keep tabs on them because the engineers are just pulling them in left and right. So in this monolithic image, you've got a different library for connectivity solutions, for root of trust, for various device drivers that come from a hardware manufacturer. If you have a DRM engine, maybe it came from China. Maybe you don't even have source code on that. You've got all of this stuff that you're compiling together under enormous time and resource pressure, and you have no opportunity to do any verification of it at all. And you can think of this a bit like a building in this case. So each of these is a brick in this building. And the problem with a monolithic model like this is, let me see if my clicker works here, is if one of these bricks gets hit, you can imagine what happens, right? The whole building comes crashing down because you have absolutely no separation in this model. So once you exploit one vulnerability in this system, you can trampoline onto the next one, and you can effectively gain root access to that system. And then you can take it over and turn it into a denial of service endpoint or any other number of security vulnerabilities. So this is why we need separation in a security system. This is the most important aspect of a security solution. So ARM introduced that 15 years ago with something called TrustZone. So in that world, they were trying to secure phones to the carrier. So I couldn't purchase a phone from Vodafone and take it across to T-Mobile and save money. They would run a rich operating system, at that point not all that rich, but a rich operating system in one side, and they would run a trusted OS on the other side of that. And TrustZone is the hardware hooks that allowed for that trust barrier to be in place. But again, as we look at the model today, this model's really challenged. Because we don't just have one thing that needs trust. We have potentially dozens of things. So maybe we have a Bluetooth stack, and we have a TCP/IP stack, and we have a TLS connection and a root of trust. So where do you put all those? If you put all of those on the trusted side, then they all can see each other's stuff. So ARM did a step forward with the CortexM version. They introduced something called a memory protection unit inside of that, which creates some additional barriers. But still, you're fundamentally hard-coded into a two-world structure here, where you have a trusted world and an untrusted world. And that's not really the design point of modern systems. A more modern design point, and one we'll talk about quite a bit today, is one where you have an unlimited number of equally secure zones. So you don't have a secure world and an insecure world. You have an unlimited number of equally secure worlds, some of which might be running small services that only run occasionally, some of which might be running rich OSs like Linux or FreeRTOS or something else. But a much more modern structure that allows you to scale with the demands of modern system creation. So let's talk about these key components of platform security here. So a trusted execution environment is the most fundamental component because it creates separation. And as I mentioned, without separation, any one vulnerability takes the whole system down. A root of trust, an ability to store keys in a way that's tamper-proof, something that you can trust, is also fundamental to this. That typically sits on top of, or sometimes in parallel to, a trusted execution environment. Secure boot prevents boot of unauthorized code. So having some sort of an immutable bootloader that's stored in ROM, which can prevent somebody from running their own code on this or getting into the system, especially if this is a system that's subsidized, where you're trying to monetize it in the back end, is extremely important. And then tools that actually work and are transparent. So a typical embedded developer spends 60% or more of their time in debug. So if you're in debug, having tools that work is extremely important. Otherwise, you tend to just give up on these solutions. Because what we find when we talk to OEMs is, for them, security is not a differentiator. Security is a satisfier. So there's some bar that they have to hit, and going above that bar gives them absolutely nothing. If you're not selling into a regulated market like a carrier or an MSO or some other structure, often that bar is very close to zero. If you're just selling a consumer IoT device, in many cases, there's nobody telling you what security that you have to implement. And under time and resource pressure, it becomes something that many OEMs will compromise. So let's get into the comparisons here. Let's talk about the hardware comparison, since we're at a RISC-V conference and this is the hardware world we live in. So let's start with ARM TrustZone A. So TrustZone A, Cortex A, is the processor that you would see in a handset or a set-top box, something running Linux or Android. So if we start out, it has 4 levels of privilege on it. It has a secure monitor, hypervisor, and then a supervisor and user. Inside of that, it has a bus which has this extra bit, this NS bit, that goes downstream, and then has filtering peripherals that are basically on the slave side of this bus. So there's a TrustZone memory adapter and an address space controller. And depending on whether you're making calls from the secure world or the non-secure world, you can configure those downstream filters to either allow the transaction or block the transaction. So that's a really simple way to think about it. It has 2 different kinds of interrupts. So in the case of a Cortex A product, you can't program the interrupts. You have 2 different kinds of interrupts. You have an IRQ, which is a non-secure world interrupt, and you have an FIQ, which you use for a secure world interrupt. So the challenge here is a couple. We really have 2 domains that are extremely hard-coded in this environment. Once you plug that NS bit, or the modern AXI equivalent of that, you're really sort of stuck with 2 worlds. It's pretty difficult to implement that in a multi-world environment. It's also pretty difficult when that starts to be multiple cores across the same bus to manage all of that structure. The second problem is when you trigger one of these exceptions. So if you try to do something that you're not supposed to do, you don't get a real-time exception back from these downstream peripherals. You get an exception that happens much, much later. So it's very difficult for you to trap that and do something useful with that information. You end up sort of blocking that and then having to go back and recover from quite a long structure. So again, this is a 15-year-old technology. For its time, it was absolutely revolutionary, but it's 15 years old. It's dated a bit. Let's look at something a little bit more recent. So this is the CortexM structure. These are the microcontrollers from ARM. So in the CortexM world, we have quite a bit different structure here. So we actually have 4 states. We have 2 states and we have 2 levels inside of each state. We have a non-secure state and we have a secure state. And then inside we have a privileged and a non-privileged level of each. We have programmable interrupts up top that you see. So you have this NVIC peripheral that allows you to program where the interrupts go and what they trigger inside of that. And then we have an attribution unit that's right on the AXI or the HB bus here in this case. And the attribution unit is analogous to the PMP and the PMA in RISC-V in that it allows you to program what comes out. And indeed, if you do something that you're not supposed to do, it'll trigger a much more urgent exception. However, downstream, you certainly can have all of these optional memory protection controllers. And in particular, that's how you would filter for secondary bus masters. So if you have a DMA controller or something else that can also write into this bus, you need to have some other memory protection controller in order to filter that, because that's obviously outside of the core's purview. Problem here is we still have two domains that are hard-coded in hardware. We still very much have a secure and a non-secure domain, although we do have quite a bit more flexibility inside of them. This is, again, a much more modern architecture. This is about a 4 or 5-year-old architecture at this point. So let's look at RISC-V. RISC-V is a whole lot simpler, and simple is really what we want to do in the world of security. So we have three privilege modes that are defined today, one that may show up in the future, but today we have machine, supervisor, and user. And we have this PMP-PMA structure, which allows us to filter transactions that go out on the memory bus. Downstream of that, for other bus masters, we have an IO-PMP concept, which some of you may have heard of and some of you may not have, but it's a way of recreating that PMP structure on other bus masters so that you can also filter those and ensure that your DMA controller can't write all over all of your other protected structure. To us, this one's really interesting because this one's hardware enforced, but now we're not really locked anymore. Now we're into the software-defined domain world. So you can think of this not as two worlds, but you can think of this as a sort of a master level, in our case, a machine level of domain, and then you can think of lower subservient level domains that we can program and configure in software. And whenever we can do something in software, we very much want to, because it's really difficult to anticipate what somebody might want to do 3 or 4 years before the chip comes into utilization. So let's talk about software. So TrustZone isn't software, but software is actually where the rubber meets the road here. So for TrustZone, there are various software implementations. Opti is probably one of the best known ones for TrustZone A, and then there's the PSA, the Platform Security Architecture, which is used for TrustZone M. And we have MultiZone Security, which is my company's product on top of RISC-V. So let's talk about Opti, which is one of the best known trusted execution environments for CortexA. So in this world, you've got a relatively complicated structure here. So you've got a TrustZone-enabled chipset at the bottom. TrustZone-enabled chipset at the bottom, you've got a secure monitor running right above the bare metal level on that. And then in the rich OS side, you've got a privileged and a user level. And in order to make a call from a rich OS down through to the secure side, you're traversing about 5 levels of different APIs and stack. It's a relatively complex thing to implement. On the Opti side here, you've got a relatively large amount of code that's running. So you've got something in the range of 250 kilobytes of code running on the Opti side, which requires about 32 megabytes of RAM to run. So for folks who are used to running Linux, that sounds like absolutely nothing. But for folks like us who are very interested in trusted code bases, that's a tremendous amount of code to trust, and ultimately a tremendous number of knobs to turn. So I think Brandon at Embedded Computing Design said it best. The design complexity of these often makes them so difficult that people just give up. And what you see for the ARM TrustZone A structure with various implementations is that they get broken, not necessarily because there's a flaw in the TrustZone technology, but because the implementations are so complex, it's very easy for designers such as Qualcomm and such as Samsung to make mistakes that are exploitable vulnerabilities. There's simply too many knobs to turn in this world. Another key challenge of this is the configuration and tools are outsourced in this model. So if you want to get a unified view of this world, if that 60% of the time you're spending in debug, if you want to be able to see this whole world at the same time, you as a user have to piece this solution together from quite a few different vendors. You can't just go to one place and download a couple tools and let you see this whole thing. It's a relatively complicated way to do security, and complexity tends to be the enemy of good security design. So let's look at the PSA model. This is the CortexM model here. So this is a much, much improved model. However, still suffers, I think, from some complexity. So in this case, we've got, in the ARM ideal model, we've got the embed OS with an application. We've got the basic SoC, which is creating some isolation on the side. And then we've got a few different layers on the secure process side. So we've got a bootloader here that's about 38 kilobytes in size, about 3,400 lines of C code, and a kernel that's about double that in size. So what that means is you're consuming 64-ish kilobytes of SRAM before you actually get any user code onto this device. So it's difficult in a very low-cost microcontroller to deploy this without sort of driving the price point of that up quite considerably. The solution ships with a TCP/IP stack whether you need it or not. It's part of the solution that comes with ARM. And the hardware today is just rolling out. So many vendors are just rolling out their first CortexM products. The first level of this PSA software is available today. The higher levels, I think, are on the roadmap for the next few years. Same thing here, unified development and debug requires third-party tools. So there's some third-party tool options that are available to give you this unified view, but they're not what easily comes together with ARM, and it's quite a complex model to put together. I think that's the general feedback from the industry. So let's contrast that with what we can do in RISC-V. So in RISC-V, we have this model of an unlimited number of equally secure zones. And we have a zero trust model in this case. So a zero trust model is a much simpler model with a much, much smaller code base. So our zero-stage bootloader is 600 bytes in this case. It's written entirely in assembly language. All it does is a SHA-256 or 512 on the next stage bootloader. That's all you really need to do in that zero-stage bootloader. The next stage bootloaders is about 4 kilobytes. Brings up the system, brings up the nanokernel, drops it into place. The nanokernel is 1.6 kilobytes in size, and it takes a kilobyte of SRAM. So it's a little bit more than an order of magnitude smaller than the PSA solution that ARM's shipping today. This is designed with formal verification in mind. You can't formally verify a generic solution. You have to have a specific implementation in mind, but the complexity of a formal verification process grows geometrically with the code size. So there's no way to do that once you get to tens of kilobytes or hundreds of kilobytes of code. This is simple. So this uses all the existing tools, GCC, GDB, the Eclipse IDE structure. So you fully compile and link these, the binaries inside of each of these zones together, and then when you want to debug them, all you do is just load the symbol files for each one. So you can be debugging across all of these simultaneously with existing tools the same way you would in a monolithic world. You don't need to buy any fancy tools or do anything else. It's compatible with all of the standard debuggers that we're all accustomed to. It's fast, so we context switch in about 120 instructions. It takes less than 0.1% of the core cycles to do this. It's universal, so anybody who is supporting the privileged extensions and has a reasonable number, and a reasonable number I would say is greater than 4 slots in the PMP structure, we can support. So this works on virtually every core that I've seen in the RISC-V world. You can just drop it in. You don't need special hardware for this. And better yet, it's open source. So you can download and play with this today. You don't have to sign a whole bunch of NDAs and go through a lot of pain before you can see if this works at all. You can drop this right on top of whatever core you're using. Let me show you how it comes together. So one of the challenges that we saw in the TrustZone world was the complexity. The number of knobs that were given to the designer was simply too high. So what we've tried to do is simplify that enormously. In this example, I've got 4 zones. And this is the sum total of the configuration that the designer gets. So the nanokernel that runs at the bottom supports both cooperative and preemptive multitasking, so you define a tick time. That's the maximum time that anybody can hang on to context for before they get preempted. And then inside of each zone, you define what resources it has. So in this case, we've assigned 3 interrupts to zone 1. So when you pull those interrupts, what happens is they're received by the nanokernel, they pull that zone immediately into context, and then the handler for that interrupt is registered at the user level of privilege. So we've taken interrupts out of machine mode, we push them up to user mode so they can't step on the rest of the security model. We've given ourselves 64K of flash and 16K of RAM in this case. We've given ourselves only read and execute access to that flash and only read and write access to that RAM. And then we've given ourselves a bunch of peripherals that we need to operate this. Zone 2 is the same thing, different flash, different RAM. In this case, we've given ourselves an Ethernet peripheral. Zone 3, same thing. Zone 4, same thing. You can keep building this, but it's a simple model. You don't have to be a security expert to understand this. And then when you're ultimately building the system, what you do is you fully compile and link this and generate an ELF file, typically. And then you run one additional step, which we call a configurator, which is a command line Java utility, which takes all of those ELF files. It takes the security file, it configures the nanokernel, and it delivers you a signed binary with a 2-stage bootloader. That all happens in a couple hundred milliseconds. It just becomes part of your standard development flow. You get a signed structure by default. So 2 weeks ago, we released this at Embedded World. We thought this was actually quite a clever demo. It got some great coverage. So what we did is we took FreeRTOS and we deconstructed it. So we took FreeRTOS in running in zone 1 and we spread it across 3 zones. We stripped the TCP/IP stack out of that and implemented it with Pico TCP on zone 2. And then you can see we terminated the Ethernet peripheral in zone 2. And then we stripped the crypto out of that. So we stripped the key management out of that and we implemented Wolf SSL on zone 3. So in this case, zone 2 is the zone that's exposed to external attack because it's really what has the Ethernet peripheral. In this case, if you do compromise zone 2, and it's Pico TCP, I think it's quite possible it could be compromised, your compromise has no ability to move laterally through the system. So you can't interrupt the real-time operations that are running in FreeRTOS. You can't get at the keys that are stored in zone 3. And then zone 4 is a backup T-console. So in this structure, we ran 3 tasks on top of FreeRTOS, and the whole thing works great. It's all up on GitHub. So with that, I will leave you with one thing that I would really like you to remember. Trusted execution environments aren't just for regulated workloads. Trusted execution environments are a great design policy for everything you're doing in RISC-V. The hooks are already in the ISA. Use those hooks, design secure systems. As David Patterson said, the state of security design in the industry is just an embarrassment right now. We really have an opportunity to do a lot better in this new ISA. With that, I thank you very much. So the question is MultiZone proprietary hex5 IP or will it be published to the RISC-V? So MultiZone is proprietary hex5 IP. It is available on GitHub. All the work that we built on top of this is all very much in the open source with an ISC license. MultiZone itself has an evaluation license today. It is our intent to open source the nanokernel itself. However, we need to get a little bit broader adoption before we do that. Otherwise, it's going to get forked and it's going to turn into a big mess. So give us a little bit of time, and our intent is to open source the nanokernel itself. The question was, can we dynamically configure the zones, or are they only done in this tool? So in this version of MultiZone, we're only allowing static configuration of zones, because frankly, the use cases for dynamic configuration of zones, I think, are a little bit nascent, and it opens up an enormous attack surface on the product. It makes the product less secure if you can dynamically reconfigure these zones. But I think once the enclave use cases are a little bit more sorted, the capability to dynamically adjust them is certainly there. We just need to figure out what level of privilege, who would you trust to do that? What's the security model around doing that? But the technical ability to do that's already in place. So if I could summarize your question, it's that for folks who come from the Linux or Windows world, Opti has some rich APIs that make development easier for them. So I think that's a fair point. The objective of what we built here is to build something that's extremely minimalist because we want this to be very trusted and formally verifiable. Any additional structures can easily be built on top of this. I think one of the criticisms I would have of an MMU-based structure is the problem is the code base that drives the MMU is typically quite large. So in some cases, millions of lines of code is driving the MMU, and that itself becomes a significant attack surface. So we need something that's much smaller and much more trusted in order to build that first level. And then, of course, we can build more abstract layers on top of that. And I would encourage you to, please. What do we need to know about the SoC in order to build a secure platform? And I think this is something that is developing inside the foundation, that there's a need to do more than just secure the core and more than just worry about the core. So I think there is a developing effort that I think Palmer's actually leading in order to develop a larger specification around securing the platform. But in the end, each platform will be different. It'll have different peripherals, it'll have different memory maps. So the system, the bootloader, has to be structured around that. We can't abstract this entirely away and keep it small size. So much like most things in engineering, there's no free lunch here. Here the focus is on building something small and secure, which means there is some customization that's necessary to each SoC platform. I think we might be out of time with that, but feel free to come chase me if you guys have any more questions.